All right, welcome everyone. It's my pleasure to introduce Tasho Kaletha, who will speak about covers of reductive groups and functoriality.
Well, thank you very much for the kind invitation. It's a pleasure to speak here. I spoke 2 days ago on the Langlands conjectures for disconnected groups, and then I decided to talk about something else here in case people are in the audience who were there on Wednesday, and there are a few. But if you are interested in disconnected groups, come talk to me after this talk. So I'm going to talk here about covers of reductive groups and functoriality. And so the basic tagline of this talk is how the idea of Langlands functoriality naturally brings you to thinking about covers. So let's start with the setup. The setup comes from the arithmetic theory. So we're going to be thinking about a base field which is local or global. So you could take maybe Q as a global field, or you could take the field of functions on a curve over a finite field, or you could take maybe a local field like the real or the periodic numbers. And let's fix the symbol for the absolute Galois group relative to some fixed separable closure. And let's consider a connected reductive group. If you're not used to thinking about a general connected reductive group, you're welcome to think about your favorite example, like the group of 2 by 2 invertible matrices, or maybe those with determinant 1, or those modulo center, or maybe you like linear algebra, so you can think about symplectic group, or maybe an orthogonal group, and so forth. So pick your favorite example. And in Langlands' idea of duality, there is an associated dual group. This is the connected dual group, which you can take to be over any field you like, and it classically is taken over the complex numbers. And so in this list of examples, well, the dual group of GL2 will be itself, and SL2 and PGL2 are going to trade places, and then SL5 and SP4 are going to trade places. And this dual group is equipped with an action of the Galois group, which sees part of the structure of this as an F group. And so with respect to that, we can form what Langlands calls the L group, which is a semi-direct product of the dual group with the Galois group. And now the principle of functoriality, which is here in the title, is the following basic idea or conjectural principle, functoriality. It says that if we're given 2 such reductive groups, and if we have a map between their L groups, then such a map should embody transfer of representations. So a map between the L groups should lead to transfer of representations. So when F is local, we are going to be looking at representations of the F rational points of H. That will be some topological group. And then they're supposed to somehow move over and transfer to representations of the F rational points of G. And when F is global, then now we'll be looking at representations of the adelic points of H. And in particular, we're interested in automorphic representations of the adelic points of H. Those should go to automorphic representations of G. And now that's a kind of a general principle, which is fairly well, its meaning is understood in this setting. And in this setting, its meaning is understood in special cases. For example, things like unramified representations. It's clear what the notion of transfer means, but more generally, it's not so clear what even the meaning of that is, let alone theorems, but it's at least some conjectural perspective or philosophical perspective. And where does this philosophical perspective come from? It comes from the second pillar of Langlands' classical ideas, which is called reciprocity. And reciprocity means that there should be a relationship between homomorphisms from the Galois group to the L group and representations of, well, G of F in the local picture or automorphic representations of G of A in the global picture. So this is the very vaguely the idea of reciprocity. And now this Galois group is the most rudimentary thing one can use, but more refined groups, maybe the Bay group, which is a cousin of the Galois group that's used in the arithmetic story, like in class field theory, or even more generally, the so-called Langlands group. That is a close cousin of the Bay group for local fields, and for global fields, it's actually not known what it should be. It's some kind of conjectural object. But if you believe in reciprocity, or at least in the idea, then functoriality becomes something very natural, because if you have now a map here that should correspond to some kind of representations, then you can compose it, and now you have a map here that should correspond to some kind of representation. So functoriality as a philosophy is kind of simply a consequence of reciprocity as a philosophy. So that's the general idea, but what happens in practice is that one is often confronted with a situation that looks a little bit like this, but isn't exactly like this. So in practice, what one has is a map which is very often injective, and this is really the main case of interest, that looks like this, where the script H is an extension of the Galois group by the dual group of H hat. But this extension is not the L group of H. Now, how can such an extension, so the L group of H is this particular extension of the Galois group by the dual group. And here we have some more general extension. So how can this identity fail? It can fail in a number of ways. First of all, this extension may just not be split. Whereas the L group is manifestly by definition a split extension. Or this extension may be abstractly split, but it may not come equipped with a split. Which means that, well, maybe you can choose a splitting, and by choosing a splitting, you can make such an identification, but that choice is now something that is auxiliary, and making different choices changes this identification. And that means it changes the way this starts to look like this. And so that means it would change the idea of transfer of representations. Or what could also happen is H may come with a splitting. So really H is a semi-direct product like this. So this now looks very good. This should be the L group, but there is another wrinkle. Now, when you have a semi-direct product like this, this means that the Galois group acts on the dual group. But the way the L group is formed is very specific, but this action need not be what is called an L action. The action of the Galois group on the dual group by which the L group is formed is a very special nature. It preserves additional structures on this G hat. It preserves what is called a pinning, which is a collection of a Borel subgroup, a maximal torus, and simple root vectors. That's what an L action is. And if you have an action that's not an L action, you form the semi-direct product, you still don't have an L group. You just have another semi-direct product. And so then, given all these various ways in which this script H differs from the L group, we have the following very simple question that maybe I'll write here. Question is, does such a map embody some version of functoriality? And if it does, who is the partner to G? It's clear that G is involved because we have the L group of G, but here we have something that maybe not the L group of H. So who is the partner? And I've kind of given away the suspense to this question with my title. But before we address this, I first want to give you a list of examples so as to convince you that this is not some kind of hypothetical situation. Not only is it not hypothetical, but in fact, it's not even a fringe case. It's actually the main case one sees. Interesting. So here are examples. The first basic example is you take a maximal torus in G. So how about we think about G being SL2R, and then S is going to be the circle, which is inside of. Then, well, actually, let me take PGO2R. For SL2, an accident happens, and there is no problem, but for PGO2, there is a problem. Then it turns out that there is either no, or at least no canonical map from the L group of S to the L group of G. In fact, in this particular case, there is actually no such map at all. But in other cases, there will abstractly exist such maps, but there won't be a canonical one given to you. There is a way to avoid this problem. So there is a workaround, which is to replace the Galois group by the Vogan group. And if you replace the Galois group by the Vogan group, what happens? The fact that in general there is no such map is recorded by a certain abstraction. And one can prove that by replacing the Galois group by the Vogan group, this abstraction is forced to vanish. Now that doesn't really resolve the problem completely, it just tells you that now that the abstraction is gone, well, there are such maps that you can choose, but there's still no canonical one. But you can choose one. And so even with this workaround, there is no canonical map. So now the set of all such maps is a torsor, in general empty, but once you go use the Vogan group non-empty, a torsor under what? Under the group of characters of the entire torus. Why may we be interested in having such a map? Well, because of functoriality. But now think about reciprocity. So the reason we may want such a map is maybe because we have some Galois parameter here, which we may want to factor and have a Galois parameter here. And then think about reciprocity. If we have a Galois parameter here, that's going to correspond to a representation of S, so a character of S. And then we might be interested in seeing what is the functorial list of that character. But if this map is only well-defined up to all the characters of S, and you're trying to extract as information a character of S, you get nothing. So that's the problem here. However, there is something canonical. What is canonical is a subgroup, which I'm going to write script S, inside of LG. Just from this data, one canonically gets such a subgroup. And this subgroup is an extension of the dual group of the torus. by the Galois group. But in general, this extension is not the L group of S. Okay, so this is the first example where we see this kind of setup happening. And if you want to think about this example that I gave here, then in this particular example, the L group of S is going to be C cross, semi-direct product with the Galois group. The Galois group just has complex conjugation and the trivial element, and complex conjugation acts by inversion on C cross. So that's a very kind of concrete, simple group. And we're trying to map it to the dual group of PgO2, which is SL2C. And technically, you can take direct product with Galois. Here, Galois actually is trivial, and you can basically forget this direct factor. All right, and you can check that there just simply isn't such a map. That's a simple group theoretic calculation. Okay. The second example comes from the theory of endoscopy. And if you haven't heard about endoscopy, or maybe you're not too familiar with it, the only thing you need to know is that endoscopy is just a special case. Yes?
Sorry, what's the script S in your particular example?
In this particular example, the script S in this particular example is going to be the norm. It's going to be diagonal matrices. Okay, let's do the diagonal matrix is product 1 in Galois, union of diagonal matrices cross sigma in Galois. This is the script S in this example. And the way this map is supposed to work is it's supposed to send the C cross tensor or product 1 here as, say, ZZ inverse. Z in C cross goes ZZ inverse. And then C cross product complex conjugation has to somehow go here. Well, I mean, this is a semi-direct product. Actually, it's enough to tell you where C cross product 1 goes. It's ZZ inverse. And then 1 product sigma has to go to something here. But sigma is of order 2. And there just simply isn't any element here that has order 2. So, yeah, that's. But if you use the Vogan group, all of a sudden, the Vogan group for the real numbers is an extension like this. And so now here you do, over complex conjugation, you have one element which is of order 4, and then also plenty of other elements. And here you do have an element of order 4. So now it becomes, but I mean, there is a more general thing about the second degree cohomology of the Vogan group valued in complex tori. The fact that this vanishes is what leads to, and you can see it in this special case explicitly. Other questions? Okay, so endoscopy is a special case of functoriality where one is given such a group script H, but also one is given a certain semi-simple element. It's not too important what this is. What is important to note is that in that theory, this script H has exactly the same shape as what I'm discussing here. It is a extension like this, and it is expressly known that it doesn't have to be equal to the L group of H. And then this eta is this embedding theory. And the reason I'm mentioning endoscopy is because how does endoscopy come about? There is a certain fundamental tool in the theory of automorphic forms for the Arthur-Selbach trace formula. And when you study this trace formula, you're led to the notion of endoscopy, and you start seeing such data. And what you see is that they look like this with this property. That is, you observe this in nature somehow. Thinking about the trace formula leads you to understand that there are such situations you have to deal with. And now, this non-equality is there even when you use the Bay group. So this workaround that at least killed an obstruction here happens to stop killing the obstruction. It's not enough anymore. So here there is another workaround, which is, well, first of all, we need to use the Bay group, but that's not enough. Then we have to choose arbitrarily an algebraic group that is bigger than H and maps onto H, which is called the Z extension. And then we have to choose arbitrarily a map from the script H into the L group of this auxiliary. So there is a lot of auxiliary choices to be made. And then one expects functorial transfer between H1 of F and G of F, no longer H. But this group was kind of arbitrarily chosen. So that leads to a lot of ugliness in the theory. You can make the theory work, but it becomes cumbersome. And one of the places where you see the cumbersomeness of the theory is in this particular example of functoriality, it's actually realized explicitly. So this functorial transfer is realized by a certain kernel function, which is a function of the product of the two groups, maybe just the regular semi-simple elements. Anytime you have a kernel function on a product of spaces, you can use it to move things back and forth by integrating away one of the variables. If you have a test function here, you can move it here. If you have an integral over a conjugacy class, you can move it here. If you have a representation, you can move it here. Basically, by some incarnation of the idea of integrating against the kernel. And this kernel function is explicit. This is the construction by Langlands and Shellstad. They give an explicit construction of this kernel function, but unfortunately, it is very complicated. And one of the reasons it's complicated, it uses a lot of auxiliary choices. And this has been one of the impediments of generalizing this theory to other situations, like, for example, the relative Langlands program that has been in discussion here, and one of the motivations maybe on this program. Spencer Leslie has been working on this, and one of the things he told me is that he doesn't have transfer factors because he just doesn't understand the construction in the absolute case. There's 4 or 5 pieces constructed separately, each with auxiliary data, and then somehow magically the influence cancels out. But there is actually a glimpse of hope because we can look at an infinitesimal version of this. So over the Lie algebras, there is an infinitesimal version that's constructed initially in the same awful way as the group version, but something interesting begins to happen. The first interesting thing, so I'm going to use my version of Gothic letters for the Lie algebras of G and H. The first interesting thing you observe is that for the Lie algebra, you don't have to make this weird choice of H1, just the Lie algebra of the original group is enough. And secondly, even though the construction is equally awful for Lie algebras, there was later work by Kottwitz who gave a very compelling and simple formula for the result of the awful construction. Kottwitz showed that if you want to, so this kernel function basically measures relative position of an element here and an element here. And then Kottwitz showed the following simple formula. One has to normalize this function, and usually one picks a pinning of the group G. Just like the dual group, I talked about L action, and it was normalized using a pinning of G hat. This is normalized using a pinning of G. And it turns out that there is a very simple cohomological invariant between a pinning of G and a regular semi-simple element of G. That's something purely on the group G that has nothing to do with endoscopy or anything. And it's something very easy. The pinning gives you what is called the constant section. The constant section meets any geometric orbit exactly once, which means that the geometric orbit of this meets the constant section in some other regular semi-simple elements. And now you have two regular semi-simple elements that are geometrically conjugate, and there is a classical way to produce an invariant out of that. Namely, all the elements of the group conjugating the one to the other are a torsor for the rational for the group, and hence they give an element of H1 of the group and as the H1 of the centralizer, and that's the topological invariance. Very classical thing. And Kopitz tells you, even though this was defined terribly, all it comes out is this invariant paired with the endoscopic element S that comes here. But the endoscopic element S has to be transported to the right place, and this is where this XH comes into the picture. So that's the end of the formula. It's a very simple, compelling thing. But no such formula was known in the group case. And so this was one of the indications that doing all these workarounds and things, some form of understanding is being lost. And then there is a final third part, which is called beyond endoscopy. So endoscopy was championed by Langlands as a first case where functoriality can be approached by adding more structure. But then around the year 2000, Langlands introduced this idea of how can we try to attack the general problem of functoriality, moving beyond the endoscopic case. And one of the basic ideas is, given a representation of G of F, or maybe G of A, the local or global case, we want to find its, so maybe we can call it birthplace. What is the birthplace going to be? Well, according to reciprocity, this representation should correspond to some Galois parameter valid in L of G. And the question is, how small of a subgroup of L of G do we need in order to capture this parameter? And so Langlands was hoping he can find some subgroup like this, which he'll call H pi, whose L group is inside of LG and captures the reciprocity parameter. But then he quickly realized that, in fact, it's too much to hope that this subgroup is the L group of something. And so if you look at his papers, he started actually replacing this notation with the notation lambda H pi. Why lambda? Because it looks like L but isn't L. So he just wanted to keep track of the fact that he cannot expect this to be an L group. And if you look at what he expects this to be, it is exactly of this kind. So these things just show up, they're forced on you, even if you start with a connected productive group and it's L group, and if you want to stick to that setting, the setting wants you to consider something more general. All right, so now that we have seen some examples of these things, let me switch gears and talk about covers. There's a corner of it that's made of diamond instead of chalk. All right. Okay, so I'll first recall for you a basic gadget called the Boro fundamental group. So here I'm going to work with H quasi-split connected reductive over F. And this is going to be related to this H hat. Okay, so what is the Boro fundamental group? It's something very elementary, but very, very useful. I won't recall the definition, even though the definition is not difficult, but for us more important will be the properties of Boro's fundamental group. So it's called pi1 of H, or sometimes pi1 algebraic. So what is it? It's a finitely generated abelian group which receives an action of the Galois group. And why is it reasonable to call it a fundamental group? Well, because when F is the complex numbers, then this literally is the fundamental group in the topological petty sense of the complex manifold, that is the complex point of H, based at the identity. But it's also useful in other contexts. For example, if F is non-Archimedean, then this fundamental group is related to the first Galois cohomology set of H. And in fact, this H can be recovered as the Galois coinvariance in the fundamental group and then the torsion part of it. And this is a functorial bijection which endows this a priori set with the structure of an abelian group. And that was one of a fundamental insight that the Galois cohomology of p-adic groups is not just a set, but in fact an abelian group. It has an interpretation in terms of the dual group in the following way. You can identify the fundamental group with the character module of the center of the dual group as Galois modules. And in fact, you could even take this as a definition of the fundamental group, but it's not a very good definition because the fundamental group is fully functorial in H. Here I'm using a different understanding of the word functorial, the classical category theory. Any map between reductive groups induces a map between the fundamental groups, which is not visible from this identification because the dual group H hat is not fully functorial in H. It has a more finicky functoriality property. So there is a different definition which makes it clear that it's functorial, and it implies this identification. All right, and now we can make a definition. We can define a new kind of fundamental group that I'm going to call pi1 tilde of H. And here is what it's going to be. I'll take the complex characters of Boro's fundamental group, which by this bullet point there is simply the center of the dual group. But again, it's fully functorial in H. And now I'm going to take degree 2 Galois cocycles in this. I'm going to treat it as an abstract, as a discrete abelian group, and then take contrary dual. So this now becomes a compact abelian group. And it's functorial in H. Okay. Good. So what is this thing good for? Here is the first theorem. It has two parts. The first part is that there exists a central extension of topological groups, which is an extension of the F points of H. Now, F being a local field has a topology, and we use that to topologize the F points of H. Now, this is a locally compact topological group, and we extend it by this fundamental group, which is also a locally compact, in fact, a compact topological group. So there exists a central extension like this of topological groups, which comes equipped with a splitting over the algebraic simply connected cover of H. So there is, it's equipped with a splitting like this. So that's the first point of the theorem. This doesn't have any content, because I could just take the direct product of those two, and it certainly will be equipped with a splitting. But the second part of the theorem is going to give a content to the first part, but for this I need the notation for from the first part, and I need a little bit more notation, which I'm going to squeeze in here. So now, given a character X of this fundamental group, it could be an infinite order character, or it could be a finite order character. And I'll be eventually interested mostly in the finite order characters, although maybe the infinite order characters will also eventually find an application. What can we do? Well, we can take this extension and we can push it out by this character. And when we do this, we'll get a new extension, which is going to look like this. Well, it's going to start with either S1 or mu n, depending on what character we have. And then it is going to end with, again, h hat as default. And if the character was a finite order, this is just an n-fold cover of this topological group, which are the covers from the title. These are the n-fold covers. Okay, so we have an n-fold cover, but we can also associate an L group to this n-fold cover. We can define LHX to be the twisted product of the dual group of H by the Galois group, twisted by this X. What does it mean to twist by X? Well, after all, X is nothing else than a 2-cos cycle of the Galois group valued in the center of H hat. By nature, such a thing is an extension of Galois by the center of H hat, and we can fatten up this extension by putting the center of H hat into H hat. And so this is this extension. All right, so that's my notation. And now using this notation, I can state the second part of the theorem, that if we assume the reciprocity conjecture, which is the local Langlands correspondence, for groups H prime connected reductive with the same adjoint group as H, so groups close enough to H, then reciprocity holds for genuine representations of this cover and parameters, Galois parameters, in this L group. Okay, so in other words, this extension isn't something stupid. It actually does encode versions of reciprocity with respect to L groups that are no longer split extensions of the Galois group by the dual group, but rather more general extensions. The proof of this theorem is not difficult. The content is somehow in the statement, in the fact that you can connect L parameters valued in non-split extensions of the Galois group by H hat to some representation theoretic meaning, namely genuine representations of certain covers. Okay, so how is this related to the problems that we started with? So let's circle back to the problem that we began with. So these are covers and functoriality. So here now G is as before connected reductive F group. And here is the second theorem. Assume, given the kind of subgroup of the L group that we saw in the examples in the beginning of the talk, let me state this precisely. So this H is supposed to be an extension of the Galois group by H hat. What does that mean? It means, first of all, that when we include H into LG and we project this to gamma, that this is surjective. This is the first condition. The second condition is if we intersect H with G hat, in other words, if we form the kernel of this surjection, and we give it the name H hat, then this is connected reductive of maximal rank, which means it shares a maximal torus with G hat. Assume this is the case, and assume that it is given, this script H is given up to G hat conjugations. This is all we can ask because the whole dual group is only well defined up to conjugation. All right, so this is the assumption. Then what do we get out of that? Then there are the following data. First of all, H quasi-split connected reductive over F with dual group H hat. Secondly, a character of this tilde fundamental group of H, which is of order 2. Now, actually, this is a little bit of a lie. I'm trying to sweep something out of the rug. There is such a character, but it's not of order 2, but I like to work with characters of order 2, so there is actually a slight amplification of this fundamental group, which I denote with a bar. So you can work with either the one or the other, it depends on your preference. My preference is for this because this tells you that the cover you're getting is as small as possible, it's just a degree 2 cover. And finally, an isomorphism from the datum that you started with to the L group of this cover. And all of this is unique up to isomorphism, and even the isomorphism is unique as much as possible. The isomorphism is unique up to conjugation by the normalizer in G hat of this script H. This ambiguity you cannot kill, it's there for a reason. But up to this, everything you get is unique. There are no auxiliary choices. And so this leads to an answer of the question we posed in the beginning. So let me repeat the question. The question was, does the embedding of script H into LG embody functoriality? And if yes, who is the partner? And the answer is yes to the first question, it does embody functoriality. And to the second question, the partner is this particular double cover, and we expect the genuine representations of the double cover are going to go to usual representations of G. So that is the philosophical answer to the question we started with. And which particular double cover is needed depends on the script H. If the script H happens to be the L group of H, then this is a split double cover, and genuine representations of the split double cover are just usual representations of H. But for other script H's, like for example, the torus in PGL2R, this is going to be non-split, and this cover will be an actual cover of that torus. Okay. So for the rest of the talk, I'd like to give 2 applications of this abstract build-up, but before we go there, maybe I'll stop for questions here. So this is kind of the end of the abstract part of just constructions before we go to applications. So are there any questions people would like to ask?
It's just very naive. You only consider like embeddings?
I only consider embeddings, that's right. The reason I only consider embeddings is because this is somehow the kernel of the problem. If you think about the structure theory of reductive groups, an embedding of one reductive group into another is kind of a wild zoo of possibilities. On the other hand, a surjection of one reductive group on another is extremely constrained. Reductive groups are almost direct products of simple factors in a torus, and any surjection is onto some of those simple factors. That's the only option. So surjections are extremely constrained, embeddings are very, very general, and a general map is a composition of a surjection and an embedding. And since the surjections are so limited, it's really the embedding that contains the difficulty. Now, of course, that's not to say that when you are in practice execute this procedure, there may be some wrinkles to sort out, probably. But this is one of the reasons I consider embeddings. And the other reason is because I'm thinking of functoriality less as starting with H and more as starting with G, and then factoring something that goes in G through something smaller. Kind of this idea of beyond endoscopy or you know, and there it's a natural thing to consider an embedding. That said, I think there will be settings where it won't be an embedding. It's certainly useful to think about it. All right, so let me tell you something about the two applications. So application one is going to be about the characterization of reciprocity for discrete semi-simple parameters. So what do I mean by this? We're going to start with a Langlands parameter, which is discrete. And semi-simple means it originates in the Weil group, not in this potentially slightly bigger Langlands group, which in the local case will be the Weil group product SL2C. And there will be some unipotent piece from SL2C, and I want the unipotent piece to be trivial, so hence semi-simple parameter. When F is Archimedean, there is no unipotent piece, and these are all the parameters anyway. But for non-Archimedean F, these are more special parameters. And so reciprocity will tell you that conjecturally there is some finite set of representations associated to this parameter. So let's call this finite set phi f, the so-called L packet. And would like to find some kind of list of properties to uniquely characterize this L packet. In the local Langlands correspondence, people construct something and say, well, this is the L packet, and then you say, why? Right? Why is you constructed something? And I'm maybe more guilty than many other people of doing this. I just say, here's a construction, and I give, why is this a construction, right? You can construct anything you want. And that is a fair question, because in the history of ideas, for GLN, there were constructions of this map, and they turned out to not be the right one. They looked nice. People were doing something that looked natural, but then they checked certain expected compatibilities, and lo and behold, they didn't hold. So something more complicated has to happen. So it's much nicer if you have a list of properties that characterizes what you're looking for, and then you try and construct it. Okay, so one of the properties is so-called atomic stability. Atomic stability, which has been in the folklore already. And atomic stability means the following, that, well, there's supposed to be finitely many members in here. And each of them has a character function, which is a conjugation invariant function on the group. So when you form virtual combinations of these character functions, you're going to get a function which is conjugation invariant. But stability says that one of those virtual combinations is even more invariant than the others. It's invariant under even more conjugation, so-called geometric conjugation. And an atomic stability says that not only does such a linear combination exist, but no smaller subset can do that. This is the smallest subset that can give you this super invariant linear combination. So let's call this linear combination S theta phi. It turns out not only does it exist, but in fact it's unique if it exists by a very elementary argument. So this is called the stable character. It's a complex linear combination of all the characters of the elements here, which has additional invariance properties. And a very elementary argument using linear independence of character tells you not only does this set determine this function, but this function determines back this set. Because you can just look at, well, what representations are needed to contribute to this function, and those are precisely the representations here. So what do we need? Now we need to specify this function in terms of phi, or some list of properties. And this is how the covers that I discussed help you do this. I'm going to, because of time is moving, I'll give an impressionistic version of it. There is an explicit formula that I'll skip writing, but if you're excited about it, come and I'll show it to you after the talk. But here is how the covers come in. So if I'm going to make an assumption now, I cannot do this in full generality, but this is the assumption. If F is non-Archimedean, I'm going to assume that G splits over a tame extension. And I'm going to assume that the residue characteristic doesn't divide the order of the biogroup. These are two technical assumptions, without which what I say will not be true. And then, well, we have this parameter we start with, and it turns out that by a very simple argument, it produces a subgroup of the L group of G. And in fact, let me write this underneath. It produces a subgroup of the L group of G through which it factors. So this is in fact Langlands' idea of beyond endoscopy in a very simple case. We found a very small birthplace for this parameter. And what kind of a thing is this? This is exactly of the kind that we're studying. But in general, it will not be the L group of a torus. But it doesn't have to be now, because now we can apply theorem 2 and get from this, first of all, an F torus. Second of all, a order 2 character of the fundamental group of this F torus. And thirdly, an isomorphism between the script S and the L group of that cover. So I just repeated what theorem 2, right here. So I just repeated the three things that theorem 2 gave us. By the way, for a torus, the bar and the tilde are the same. So I literally have the thing that I told you about here. Well, but what does that mean? That if this is isomorphic to the L group of this cover, I have this parameter, it canonically factors through here, it canonically continues here. So without any auxiliary choices whatsoever, I get a genuine character of this double cover. Right, that just comes out of the parameter. And now, this is what I'll keep telling you. There is some explicit formula that I can write for this function in terms of this data. And I'm happy to write it down for you after the talk. It will take a minute or two. And that's it. That uniquely pins down this function, hence pins down this set. And the funny thing about this formula is that it is uniform for all local fields in a suitable sense. It works for real numbers, works for periodic numbers, works for function fields. And for the real numbers, it recovers the formula that we know because their reciprocity has been known for a long time by Langlands himself and then refined by Shellstad. We know exactly what this function looks like. And the same formula in a suitable sense also works over non-Archimedean fields. Okay, so that's one application. And the other application is to endoscopy, which, if you remember, that was our second example. So we start with an endoscopic datum, which I'll remind you, bits of it was you have exactly such an extension of the Galois group by the dual group, and this data embeds it into LG. And in the classical setup, you are forced to choose a Z extension and things like this. But now all we do is we just apply our theorem 2 again. And we get the quasi-skewed group H. Well, it was recorded, so that's nothing new. But we also get this order 2 character of the fundamental group. Hence, that gives us a double cover of the rational point. And we get the isomorphism from, let's say, LH to script H. So we get this for free. And then what does that mean? We come here and we see, well, endoscopy should tell us that we need to transfer genuine representations of these natural double cover representations here. This is what the endoscopic functoriality should be. But remember, functoriality for endoscopy is realized by a kernel function. So there should be a what is called the transfer factor should actually be defined on the cover now, and not on the group itself. So the question is, can we realize the classically constructed kernel function by Langlands and Schaustad in this situation of covers? And the answer is not only yes, we can, but in fact the construction simplifies. It's not a bunch of individual pieces all depending on auxiliary choices. Instead, it's just a product of two pieces, none of which depends on auxiliary choices. There are two pieces that have meaning on their own right. And one is for G, and the other one is for LG. So there is an invariant on the side of G, there is an invariant on the side of LG. You take their product, this is your kernel function. And let me try to just very briefly give you the flavor of what these invariants look like. Remember that for Lie algebras, the whole Lie algebra transfer factor was interpreted by Kottwitz as there was some natural invariant between a pinning and a regular semi-simple element of the Lie algebra, and that was paired with S. So that was Kottwitz's interpretation of the transfer factor. Well, this is exactly what number one looks like. Number one looks like this. Well, I mean, you can ask yourself, can this invariant, can I descend it through the exponential map to a neighborhood of the identity in the group and then globalize it to the whole group? And the answer is no, that doesn't work, which is why in the classical transfer factor, such a formula wasn't there. But what turns out to work is that there is a natural invariant between a pinning, the same kind of pinning because the pinning is for the group, and an element. This is a regular semi-simple element, not on the group, but in a cover of a maximal torus. So regular semi-simple elements in reductive group live in tori, but this invariant cannot take a regular semi-simple element in a torus, but it can take a regular semi-simple element in the cover of a torus. And now if you think of the exponential map, the cover of a torus has the same Lie algebra as the torus itself. It's just a finite cover. So infinitesimally, they look the same. And the exponential map to the group factors to an exponential map to the cover and then down. And even though this invariant doesn't descend to the group, it descends to this particular cover. And not only does it descend, but in fact, it globalizes to the whole group. In other words, this invariant, when you compose with the exponential map around the identity, becomes this invariant. And that's number one. You just pair this invariant with S exactly in the same way. So that's it. But it turns out that there is a second piece which is not visible in the Lie algebra, because the second piece is a character with an open kernel, and when you go to the identity element, you only hit the kernel. Where does the second piece come from? Well, it comes from the following simple diagram. You have the L group of G, you have the L group of the cover of H, and there is a canonical map here. This is what theorem 2 tells you. Now, we have the max, and this function here is constructed by matching maximal tori in G and H. This is how functoriality in endoscopic terms works. So there is a maximal torus that you're interested in G, and there is a maximal torus that you're interested in H, and they have been identified. This is just in the inner workings of endoscopic functoriality, this is the setting. Well, if you use the covers of these tori, there is a canonical L embedding here, and there is a canonical L embedding here. This was our first example about L embeddings. And now it turns out this doesn't commute, it commutes up to a very simple shift, and this shift gives you a genuine character. Genuine character of a cover of S. And those are the two things. There are no choices anywhere. And not only that, but if you look closely, you see that most of it is not even endoscopic. This has nothing to do with endoscopy. This is just a general functoriality business about L groups of So this doesn't have to be the L group coming from endoscopy. This just came from theorem 2. We applied theorem 2 to an endoscopic situation, but theorem 2 didn't care about endoscopy, and this S doesn't play any role in theorem 2. So we can apply this to any functorial setting. This makes sense in that generality. And this invariant is something intrinsic to G. The only place where endoscopy is seen is this little element S here. That's it. So I suspect that these pieces will find their way in general functoriality considerations. But yeah, that's all I wanted to say.
Any questions or comments?
Is there any relationship between the Boro fundamental group and the ATOL fundamental group G as a scheme?
I don't know. I don't. Well, the tau fundamental group of G as a scheme over the complex numbers would become just the Betty fundamental group where they are the same. But what happens over general base, I am not sure. I mean, first of all, no, I don't have anything intelligent to say.
Are there any questions from the audience online? Please put them in chat or also say them out loud if you'd like. Any questions from our group here?
So the first pairing, if in the split case, it's also new.
Yeah, it does. You mean this thing here?
Yes.
Yes, this is. I mean, I don't know what new really means. Somehow the shadow of it was present in the computations that Langlands and Schaustad did when they defined the classical transfer factor. I kind of just tickled it out of there and realized that it gives you an invariant like this. But you could say it's really their insight that there is a certain computation one can make, except they didn't understand that it has to do with covers and it's an invariant like this. But more to your question, it doesn't matter if the group is split or not. Yeah, this really is a non-trivial thing in any case. For SL2, it's a non-trivial thing. Yeah.
So you propose a characterization of the local Langlands correspondence. Is it clear that proposed constructions of the Langlands correspondence satisfy this characterization?
Right. So yeah, the construction that I have proposed does satisfy it, and that's kind of in hindsight in the sense because I first proposed the construction, and it seemed very natural to me, but it wasn't clear why. And then eventually I realized that my guiding principle was the character formula. And then only later did I realize these covers are floating in the background and one can use them to interpret what I had done in a more invariant way, where I had again made some auxiliary choices and then by magic they canceled out and I didn't understand why. But then from the point of view of the covers, it was completely clear why, because the choices I had made was there to just trivialize the cover. And then at some other point, I untrivialize it again, unknowingly. But if you actually use the cover, you see you're just doing something superfluous and you can just not do it. And then, but other constructions, like for example, the Fark-Schulze construction, it's unclear how to see character formulas from that construction at this point. So I think the answer there is not clear. There have been connections between the two constructions for various groups, for unitary groups or for SP4 and things like this, and there, then you can say something.
This is a vague question, but I mean, this pylon tilde that you've written down, there's some sort of double dual that's happening. To this. Can you contextualize that a little bit?
Yeah, I don't know if I have anything intelligent to say about this. It's the double dual is so that on the dual, so you go dual and you go back. But when you go dual is where you take the Galois cohomology.
Right.
And so I don't see a way to do it without going dual first. And also I want to connect to the dual because somehow the game is played on both sides at the same time, on the G side and the dual G side. So going there and back somehow connects them in some first step, because you have covers, but you also have L groups of covers. So these happen on the dual side, and these happen on the non-dual side. And so there is some kind of communication between these sides throughout the story. But I realize this is a very vague answer to your question. I don't have a more compelling thing to say at this point.
It was a vague question, so.
Yeah. I do want to say something, which is that, and I should have said it already when I stated theorem 1 about the local reciprocity and the existence of this extension, which is that there was prior work which was on this subject, which was really a guiding force for me. So there was about theorem 1, there was work of Adams and Vogan from 1992 over the real numbers, where they obtain results that are very similar. They obtain such a fundamental group, that pi1 tilde. They obtain an extension of H of R by this fundamental group. And by push-outs, they have covers, and they obtain the reciprocity for these covers. So all of this was there. And what I do here, you can think of generalization to any local field of what they do, except that when you apply what I do over the real numbers, you don't exactly get what they do. So their pi1 is a discrete abelian group. My pi1 is a compact abelian group. And I can compare the finite order covers coming from both places. And I can show they're canonically isomorphic, and I can show the local reciprocities agree for them. But the infinite order covers from my picture and their picture, I don't know how to compare. So our kind of big extensions are only comparable in some roundabout way. It's not exactly the same. And the reason is because I didn't just straight up generalize what they did. I don't know how to do that. Their arguments are very real Lie group theoretic. So my arguments are quite different. But then in hindsight, you can compare the two pictures of the real numbers and see that they're close to each other. But their results were really guiding force for me, because when I saw them, I thought maybe something like this is possible over an arbitrary local field, not just over the real numbers, and it would answer a lot of natural questions. So I should have stated that already there.
Okay, we have a comment from the audience, online, which is about relations to physics, which I'll pass on to you afterwards. But let's thank Tasho again, and we'll end the recording at this point. So let's thank Tasho.